Good day, friends. Today I shall talk about my PhD thesis. I did my BStat and MStat from Indian Statistical Institute in 1987 and 89. Then I did another Masters in Statistics from University of Rochester, New York, and I joined software industry in 1997. I could submit my PhD thesis in 2005, and in 2007 I got awarded the degree. So it took 18 years for me, starting from 1989 when I completed my first masters to getting the PhD. It took 18 years. It's a long time. Anyway, I could do my PhD, and today I'm going to talk about it. The title of my PhD is Some Contributions to Two Estimation Problems: Estimation of Common Mean and Size of a Finite Population. So there are two problems. One is estimation of common mean, and the second one is estimation of size of a finite population. So part 1, estimation of common mean; part 2, estimation of size of a finite population. So let me start with part 1, estimation of common mean. So let's start with an example. Suppose we are monitoring gasoline quality based on read vapor pressure using two methods. The first one is a cheap and quick method yielding crude measure obtained on site. Say I have got 10 samples there, and an expensive laboratory analysis yielding a measure of presumably higher precision. Say I got 10 samples here. Now in this problem, under normality assumption, we know sample mean is the best estimator for the gasoline index. It is uniformly minimum variance unbiased estimator, UMVUE. But when you combine the two samples, when you consider 20 samples altogether, there is no best estimator. It has some theoretical proof that the problem is not complete, so we don't have any best estimator or uniformly minimum variance unbiased estimator. Greville-Deal in 1949 proposed an estimator that's a weighted average of the sample mean with weights inversely proportional to sample variances. So that's Greville-Deal estimator 1959. It's a good estimator. I mean, it works well. So today researchers are working on two main lines. One is finding good properties of Greville-Deal estimator, and two is finding estimators that are not beaten by Greville-Deal estimator, that doesn't fall below the Greville-Deal estimator power curve. So I mean, nobody can think of an estimator which uniformly beats Greville-Deal, but at least it is not beaten. It's for some population parameter it's better than Greville-Deal. Some population parameter it's less efficient than Greville-Deal. So there are two lines. One is finding good properties of Greville-Deal estimator, and another is finding estimators that are not beaten by Greville-Deal estimators. So in my work in chapter 1, I found an admissible class of estimators of common mean, and the paper came out in 1995 in Calcutta Statistical Association Bulletin on a class of admissible estimators of common mean of two univariate normal populations. So that's chapter 1. In chapter 2, I used two-stage sampling to develop Greville-Deal type estimators of common mean. I introduced two-stage sampling and did some work, and the paper came out in 1998 in Calcutta Statistical Association Bulletin, estimation of common mean of two univariate normal population using two-stage sampling. So that's chapter 2. In chapter 3, I introduced covariates method and developed various types of estimators of common mean. So chapter 3 deals with the introduction of covariates in the model, and I presented the paper in 1999 in Calcutta University Triennial, estimating the variance components of the common mean of normal population in presence of covariates. So that's chapter 3. And in chapter 4, I used a cost constraint in the model. There is cost of sampling, so we considered that and developed optimal sampling schemes for estimating common mean. So everything goes around the common mean topic, and the paper came out in Journal of Applied Statistical Science in 2005. Optimal sampling scheme for estimating the common mean of average normal population under differential sampling cost. So that's the 4 chapters on common mean, and uh, that completes part 1. I'll stop here, and in my next episode I'll talk about part 2.